Let's take a look at sketching graphs using all the tools that you've been building up, which is things like the first derivative, the second derivative. What's a critical point? What's a point of inflection? All those things we're going to use in building our graphs. So first of all, to build a graph, we can still use our old regular techniques. Things like figuring out what the intercepts are. What are the discontinuities? Are there asymptotes? Using those is still going to be important information. But we want to build upon this. So we want to use things like the first derivative. So the first derivative, as we saw, the two main things we can find out are the critical points, so where the slope is changing basically, from positive to negative, and just your intervals of increasing and decreasing. With those critical points, we can also identify, are those critical points local maximums or local minimums using the first derivative test. You could also optionally instead use the second derivative test, because you're most likely going to be calculating the second derivative as well. So it's just a matter of preference which to use. The second derivative, we're going to use that to figure out things like inflection points and what our concavity is like. So concave up and concave down. And then, again, the last part is just optional, because you might have already done the first derivative test, so you don't necessarily need to do the second derivative test then. So it really depends on what your preference is. Using that information, we can make a much more accurate graph than what you would have done previously. And yeah, you'll not always need to use all these steps. Not every graph is going to have an asymptote. You're not always going to have to do the second derivative test if you did the first one. So, but these tests will all help you to build an accurate graph. So let's start with a polynomial, something familiar, not too difficult. So first of all, let's just take some derivatives. I always like to just calculate the derivatives out, just fully first of all, and then can analyze those separate parts. So we're going to have negative 3x squared plus 12x minus 9. And that's going to be negative 6x plus 12. Okay. So some quick derivative work. Now let's just go through in order what we want to find out. So let's start with the original function. So the original function is just what we have there. Let's factor that to get the x-intercept. So we have, I'm going to factor out a negative x squared plus 6x, minus 6x now, plus 9. And then that trinomial is just x minus 3 squared. So x-intercepts of x equal to 0, that's order 1, and x equal to 3, and that's order 2. Other information that we would have used regularly is what's the degree of the polynomial, what quadrants is it going between, so f of x is degree 3, and it has a negative lead coefficient. So it's going to be ending going towards negative infinity because of that negative lead coefficient. And so it's going to go from quadrant 2 to quadrant 4. All right. And the last piece of information is the y-intercept. So the y-intercept, well, in this case, plugging in 0 just gives you 0. So not much to do there. That is what it is. So there we have it. We have information about the graph from the original function. You could have graphed this using what you've done before. Now we're going to build upon that. So we're going to use that first derivative. And let's take that first derivative and factor it. So factoring that first derivative is going to give us, well, let's take out a negative 3. We're going to have x squared plus 4x minus 3. And that's actually pretty simple to factor now. Just going to be x minus, I was going to say something doesn't seem right. It's because we factored a negative 3, so Switch those signs. Now things make more sense. X minus 3, x minus 1. That's better. All right, so f prime of x equals 0 at x equal to 3 and x equal to 1. So we've got our critical points. There's no undefined areas. So let's figure out our intervals of increasing and decreasing. So we will set these critical points on our number line here. I'm just going to put in some test values. Again, it's not like I'm actually going to figure out the value of the function. I just need to know what the sign is. And so f prime of x is going to be, well, let's see this. So if you plug in 0, you're going to have a negative, the negative 3. 0 minus 3 is negative. 0 minus 1 is negative. 3 negatives gives you a negative answer. Plugging in 2, start with a negative from negative 3. 2 minus 3 is still negative. 2 minus 1 is now positive. So that's positive. And plugging in 4, you have the negative to start off with, positive, and a positive gives you a negative in the end. I like to sometimes draw, again, just the shape of what that means. So negative slope, positive slope, negative slope. So you can see that we kind of have the u and the upside down u, which means x equal to 1 is a local min, x equal to 3 is a local max. Okay, so we've got that information. Now we also want information about our second derivative, so the concavity. So we've got the second derivative up there, negative 6x plus 12. Let's just factor that. So negative 6, x minus 2. So it equals to 0 at x equal to 2. We'll do a little mini table this time, or number line. Basically look to the left and to the right of 2. And so f prime prime is equal to, well, plugging in 0, negative times a negative is positive. Plugging in 4, negative times 4 minus 2 is 2. Positive is negative. So it's concave up to 2, and then it becomes concave down. All right, so let's go ahead and graph this out. So what I'm going to do is I'm going to start going back to the original function. Let's plot the intercepts and the y, well, just the intercept. So we have 0, 0, that's both an x and a y intercept. And we have x equal to 3, or order 3, or order 2, I should say. Intercept. All right. We also have a local minimum at x equal to 1, local maximum at x equal to 3. So when we begin drawing this, we'll keep that in mind. And yeah, we've got our concavity at x equal to 2. So I'm just going to label 1 and 2 on here, just so that we know we have to think of something special there. The last part is the quadrants that we're going in. So we're going from quadrant 2 to 4. So we're going to start in quadrant 2, going downwards, and following both the intervals of increase and decrease, we're going down and we're concave up. So it's going to look like a U shape. And it's kind of tricky sometimes to get it accurate. And eventually we're going to hit a local minimum at x equal to 1. So that's what I'm keeping in mind here. Local minimum at x equal to 1. And in fact, you know what's best? Is to figure out the coordinates of those local minimums and maximums. So let's do that here to the side. So f of 1, f of 3. Well, I'm also going to do the inflection point. So I should have done this at the start, but let's do that now. So f of 1 is going to be negative 1 plus 6 minus 9, which is going to be negative 4. F of 2, plugging in 2, you're going to get negative 2. And f of 3, well, that was one of our intercepts, so it's just 0. All Now we can really make this as accurate as possible. So our graph is concave up, and it's going to reach -4. So I'm going to plot that point here, -4, and we're going down to that concave upwardly, like that. Then at -4, since that's the minimum, we go back up, still concave up, and eventually at 2, -2, that's when that U shape is going to turn direction. And then our U shape is going to turn to go concave downwards. And where are we going to go towards? We're going to go towards the next local maximum, which is the 3 there. And then we go, and we're concave down the rest of the way, like that. And there you have it. We have a more accurate graph than we would have had before. All right, so let's use these techniques to try out the next graph. So as we go on to the next graph, we already have our derivatives given to us, just to save ourselves some time. So let's figure out some other information. So we have a rational function. So with a rational function, we can still figure out things like x-intercepts, so on and so forth. So we're going to want to do a little bit of factoring. So to factor this, we can factor out a 2. And then that's going to become x minus 4, x plus 1, x minus 3 squared. Right, nothing cancels out, so no holes, but we do have a vertical asymptote. So a vertical asymptote at x equal to 3. Horizontal asymptote, let's double check that. So we have something that's degree 2 in the denominator, and something that's degree 2 in the numerator. So it's just the leading coefficients that we need to look at. And in this case, you have a 2 in front, nothing in front of that because it's just x there. So the horizontal asymptote is y equal to 2. All right. So again, that's lead coefficients. Continuing onwards. So continuing onwards, we can look at the intercepts. So the x-intercept, the y-intercept. So for the x-intercept, that's going to come from your numerator. In this case, that's going to be x equal to 4 and x equal to -1. Your y-intercept, well, that just comes from plugging in 0. So if you plug in 0, you're going to have -8 over 9, actually, if you plug that in and calculate it out. Because the 3 squared in the denominator becomes 9. Okay, we've got some good number of points there. Since we have a horizontal asymptote, we could check, does it cross that horizontal asymptote? That can sometimes be handy. So let's do that. So cross HA. Well, what's the horizontal asymptote? The horizontal asymptote is y equal to 2. So check if y equals to 2. So I'm just going to set the equation equal to that. And then we can just see, can we solve this equation? So we just have to move the x minus 3 up. Then we're just going to want to expand that out, essentially isolate for our x's. So x minus 3 squared is going to be x squared. Then minus 6x times 2 is going to be minus 12x. -3 squared is 9. Double that is 18. Okay, 2x squared cancels 2x squared. That's nice. Let's move over 12x to the right. 26 is 6x. So x is equal to 26 over 6. That can definitely reduce. That'll be 13 over 3. Okay. So crosses horizontal asymptote at 13 over 3, 2. Okay, so we've made use of our regular function to figure out some information. Now let's make use of our derivatives. And you're going to see we didn't even do our asymptote behavior because information like our derivatives will actually help us with that. Okay, so the first derivative, dy by dx, set that equal to 0. And since it's factored, it's just, we'll look at that factor, 17/3. And since it's at 17/3, we could include a number line, but we also need to remember, check where things are undefined. So also check your vertical asymptotes. So undefined at x equal to 3. And so then we want to include both of these on our number line. You could also make a table some way. Oh, 17/3 is bigger than 3, so I should order this correctly. And test some numbers. 17/3 is a little bit bigger than 5. So we'll do something like that. And now let's just check our signs. So what is the sign of f prime of x? So in the first case, when you plug in 0, you're just going to have, well, a negative times a negative, and it's cubed, so it's going to be a negative. So that tells us this is going to be all negative in the end. Okay, plug in something like 4, negative 2. 3 times 4 is still smaller than 17, so that's going to be negative in the numerator. 4 minus 3, though, is now positive. So we do end up getting a positive there. And lastly, we have a big number where you have a negative in front times some positive over some positive. And so then we get a negative in the end. So overall, we can see then it's going down, then up. It looks like a minimum there, then back down. We do have to be careful, though. What's the undefined part? So remember, x equal to 3 is the vertical asymptote. And then x equal to 17/3. Well, it's going down and then up, or sorry, up and then down, is a local max. So that's our first derivative test. Continuing along, we are going to just figure out what the value is. The y value may as well. Okay. Plug it into your calculator. If you plug it into your calculator, you're going to get something like, I'll just write the answer down, 25/8, which is approximately 3.13. Or 3.125, but to 2 decimal places. So 17/3, 25/8, or I'll do the approximate values, 5.67, 3.13. And that's just going to help us to figure out exactly where it is on the graph, because sometimes fractions are a little hard to visualize. Okay, lastly, the second derivative. So let's figure out what d squared by dx squared is, and we have 12x minus 7. I'm just going to rewrite it down here. X minus 3 to the 4. So we can start off with when is it 0. So 0 at x equal to, well, let me just be careful. It was, okay, I wrote that down correctly. So x equal to 7. So that works out nicely. And then also, when is it undefined? So, because things might change there. Undefined at x equal to 3. So again, let's make one last number line. Put in 3, put in 7, test out some values, just to see what the sign is. So f prime prime of x is going to equal, and let's just test things out. So putting in 0. You have some number 12, which is positive, times 0 minus 7, which is negative, times 0 minus 3 to the power 4, though. So the denominators are always going to be positive. So we have a negative answer there. Okay, plugging in 5, 12 is positive. 5 minus 7 is negative over a positive. So again, negative. And then the last part, plugging in some big number. Well, everything's going to be positive then. So the answer is positive. All right, so let's begin plotting our function. So our function has a vertical asymptote and a horizontal asymptote. So let's draw those down. Draw it nice and neatly with a ruler. So there's x equal to 3. And there's y equal to 2. Could be a little straighter. That's my fault. We have our x-intercepts. So 4 and negative 1. And what other points do we have? We have a crossing of the horizontal asymptote at 13 over 3, which is just a little bit bigger than 4. Should say 13 over 3, 2. Then we have that local maximum at 17 over 3. So as we saw, that's about 5.67. 3.13, so we'll do it approximately up there. And we have our point of inflection at 7. Okay, so I did leave things a little tight here on the graph. And at 7, let's figure out what the value of the function is at 7. Okay, plugging in 7 into your calculator, you will get 48 over 16, which is just 3. So it works out to a nice number. Okay, so I should have left myself a little bit more space there, but let's go through things now. So let's work on the left side. So on the left side, we know it is concave down, looking at the intervals. We also know that it is decreasing up to 3. So everything's kind of happening up to 3. So decreasing concave down, and it crosses that. So essentially that means we're going to be below the horizontal asymptote. Go through that. Oh, we also have a y-intercept. The y-intercept was negative 8 over 9. So let's just include that. Through the y-intercept. It's not the smoothest. Let's make that a little more smooth. And then towards the horizontal or vertical asymptote. Arrows on the graph. Then on the right-hand side. So on the right-hand side, we are increasing, taking a look at our interval up here. So we're going up from 3 until we hit that local maximum. And as well, this whole time, we're going to be concave down. So we're curving. Our slope is becoming less and less and less and less. Curving downwards, downward, downwards. Then we hit the inflection point. And this is where we switch direction. Now we have a regular U, and this is what's going to make it approach from above, like that. So our asymptote there is approaching from above after we have that concave up shape happening. And there is our graph. All right. So yeah, doing these kinds of graphs, it does take a little bit of time, but the idea is first and second derivative can give us that extra information to make it that little bit more accurate. So let's do one more. So let's calculate some derivatives and then get some other information. So f prime of x, well, x ln x, going to have to do a product rule. So it's going to be ln x plus 1 over x times x, or ln x plus 1. And then second derivative is just going to be 1 over x. Okay, so we've got that. Now let's go through kind of the individual parts. So the original function, if we take a look at it, well, ln of x is only defined when x is greater than 0. So I'm going to actually just use set notation here. So we just have to make sure, first of all, that we're always just looking at greater than 0. In terms of x-intercepts, well, when does x ln x equal to 0? Could be at x equal to 0, but not in domain. Or it could be at x equal to 1, because that's when a logarithm is equal to 0. Okay. And then the y-intercept, well, can't cross the y-axis if we're never equal to 0 in terms of our x value, so none. All right, let's further analyze the first derivative. So the first derivative was ln of x plus 1. So let's just check when is that equal to 0. So rearranging that, -1 is equal to ln of x. Or converting that, e to the -1 is equal to x, or x is equal to 1 over e. All right. So it's also not undefined for any point that's outside our domain. So let's do a number line with that. So 1 over e. So something bigger than that is just going to be, well, let's think of 1. 1 over e is about like 0.3. So I'm just going to test 0.1. And so then doing that, testing our first derivative, what you'll end up having. In this case, it's a little harder just to actually just know what it is using your signs. So you can just plug in 0.1. If you plug in 0.1, what's going to happen is you will get a negative value. If you plug in 1, ln of 1 is 0, plus 1 is positive. So it's going downwards and then going upwards. That also tells us then that 1 over e is a local min. And not only that, let's figure out what the value of the function is there. So plugging in 1 over e into that original function, well, that will just give you, well, the ln of e, 1 over e is just -1, so it's -1 over e. So it's the point. 1 over e, -1 over e. All right. And so then the last part we want to double check is the second derivative. So we saw that the second derivative is equal to 1 over x. So it's never 0 but undefined at but really that doesn't really matter because that's outside our domain. So for x greater than 0, f prime prime of x, plugging in some number bigger than 0, it's going to give you a positive. So always concave up. All right, so let's go ahead and graph this function. So graphing this function, what we're going to have is we're going to have a intercept at 1. I'm going to draw a hole at x equals 0 because, as we saw, like the logarithm isn't defined there, but you had that x part, so it was like it would be approaching there, but it's just not actually defined there. And then we have at 1 over e, which is, let's say, about a third. It's not quite that. And -1 over e. So 1 over e, negative 1 over e, we have that local minimum. So our function is decreasing up to that local minimum and then increasing afterwards, as we saw by the first derivative. And it's always concave up. So it's going to decrease in a U shape, go upwards, 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 and it will keep up that U shape because it's concave up. And there we have it. That is our function. And that's just in general how we draw a function. So we can draw any kind of function. You saw here we drew ln x times x. That's not one you would have looked at last semester or whenever you took advanced functions. But we can draw it using the first and the second derivative.